All right, in this video, we're going to be looking at applications of the definite integral. And the first application that we're going to be looking at is actually something that we've done already before. We are going to be looking at distance versus displacement. And this section uses a little bit different language. Distance, they're looking, or they're calling total distance. Whereas displacement, same idea, but the language that they're using for this section is net distance. So we understand that displacement is just our change in position, whereas distance is the total amount that you traveled. Okay, so let's start off with a doozy of a problem. We've got this car trip, and the velocity is given by this following trig function. And let's think about um, graphing this trig function because we need to figure out how far the car traveled during this trip. Well, what are the effects of all this? Well, let's first talk about the period. We know that in a trig function, the period is 2 pi over this value. Well, that value is 2 pi. So our period is 1, which means in one, from 0 to 1, and that's actually what we're looking at from 0 to 1, we're going to go the full cosine cycle. And what's the effect of this? Well, that's our amplitude. And the negative is going to reflect it. And the 25 shifts it up. So if we think about our typical cosine graph, where this cycle is usually 2 pi, now the cycle is just 1. And the 25 is going to make us go from 25 to negative 25. And the negative sign is going to cause us to flip. So it's actually going to look like this. And then the plus 25 is going to shift our entire graph up by 25. So we end up getting the real graph, which is in blue, will look like this, where we're ranging from 0 up to 50 now. And if we're looking for so this is a graph of the velocity function. And now if we want to determine how far the car traveled, we need to find that area. So first and foremost, let me just acknowledge that while this is a difficult thing to graph potentially, you are expected to be able to graph these trig transformation functions. So if that's something that's hard, note it. Maybe send an email to me or whoever your most helpful teacher is, and say I need some help with graphing trig functions and get that help. Well, anyway, so now to find the distance, which is also the displacement. In this case, distance is displacement since we're not changing direction. It's always above the x-axis. Our distance is going to be the integral from 0 to 1 of 25 minus 25 cos of 2 pi t. And at this point, this problem becomes really just a, um, a straight up definite integral problem with a little bit of a reverse chain rule. Um, so this will equal 25t minus 25 over 2 pi sine of 2 pi t. And we're evaluating this from 0 to 1. Now, while this looks kind of tricky to evaluate, it actually comes out quite nice. We get, oh, that should be 25t. So we get 25 times 1 minus 25 over 2 pi sine of 2 pi minus, well, now plugging in 0, this term would be 0 minus, and this term is also 0 because sine of 0 is 0, and sine of 2 pi is 0 as well. So that's also 0. So what we get left with is just, what we're left with is 25. Welcome to the party, people. That's a hard problem to get started. So let's just talk about what we did. First thing we had to do is we had to understand graphically what's going on. So a trig transformation problem. Once we were able to graph it, then we said, okay, well, to find the distance, we find the area underneath it. So we integrate. We had to do, a little bit of clever integration by dividing by this 2 pi to accommodate for that 2 pi there. And then we just evaluated our definite integral, and knowing what we know about sine, we get our answer. Let's look at a slightly easier problem, though. First, though, net distance, which is equivalent to what we've been calling displacement, is the integral of the velocity versus total distance traveled, which is the absolute value. And just as a reminder, if this is our velocity vector, and so here's my velocity, and I want to integrate from A to B, the key thing, if I'm trying to find the total distance, this would equal, let's call this point C. It would be the integral from A to C of V of t dt minus the integral from C to B. And it's minus because this integral will be negative, and so minus what will be a negative will make it plus, so we're adding up all the distance. That's the total distance traveled. Versus displacement, which is just simpler, A to B of V of t. It's always nice when things rhyme. Rhyming just feels nice to say. So, I mean, you could try that. The integral of A to B of V of t dt. That's nice. All right. So here's a much easier problem than the first one we started. It says find the displacement and the distance for an object moving with velocity v equals 2 minus t. Well, and we're looking from 0 to 4. So we know what this graph looks like. This is just a nice and easy linear function. And this is 2, and this is 2, and we're looking all the way to 4. So this red area is positive, and this blue area, let's call it, the blue area is negative. And geometrically, it sort of looks like our displacement might be 0 because these areas, it looks like we'll cancel each other out, but let's prove that. So our displacement, or our change in position, equals the integral from 0 to 4 of 2 minus t dt. Well, this equals 2t minus t over 2, t squared over 2, evaluated from 0 to 4. Well, the 0's going to go away since when I plug 0 into t, it's nothing. So the only term we're looking at is the 4. And as we expected, our total displacement is 0 because we walked the same amount in the positive direction as we did in the negative. But what about the distance that I walked over that time? Well, our distance, the total distance, would be the integral from 0 to 2 of 2 minus t dt minus 2 to 4 of 2 minus t dt. And here's where we can be clever. Since we know these areas are the same, all we need to evaluate is one of them and then double it. So let's go 2 times 0 to 2, 2 minus t dt. And we take the antiderivative, so we get 2 times 2t minus t squared over 4 from 0 to 2, and plug in. So 2 times 2 times 2 minus 2 times, or 2 squared over 4. And this equals 6. So that's the total distance that I traveled, which means this had an area of 3 and this had an area of 3. Oh, I knew that didn't make sense. Sorry. Um, this should have been a silly mistake. This should be 2 here, not a 4, and a 2 here, not a 4. Now this works out nicely. So this is 2 times 4 minus 2, which isn't 6, but it's 4. Yeah, that makes sense, which gives each of these an area of 2, 2, and 2. And you can see that geometrically. It's just a triangle, 2, 2, half that, you get 2. And add up these 2 and 2, you get 4. Ah, that makes sense. Good. All right, now let's do more of these problems. It says an object moves along a coordinate line with a distance to the right being positive. Here's our velocity function over the time interval 1 to 3. We want to find the net and the total distance traveled. And we're doing this all by hand. So the first thing we need to do is find out where this equals 0. So if we factor it, we see that we're going to have zeros. That's 10 because of my y-intercept. And I'm going to have a 0 at 2 and at 5. So my graph is going to look something like this. 2. And the key thing is that I'm looking at the interval from 1 to 3. So I'm looking at, if this is 1, that's that area plus this negative area. So when I find the net distance, I don't really need to worry about that for the net distance. For the net distance, it's just 1 to 3 of t squared minus 7t plus 10 dt. And doing the antiderivative, we get t cubed over 3 minus 7 over 2 t squared plus 10t. And we're going to evaluate that from 1 to 3. And just, you don't need to see me do that. You can evaluate that. So I'll leave it as that. That's the net. To find the total distance, now we just need to do where we split up the integral. So from 1 to 2, and I'm choosing 2 because that's my point where I change direction. So 1 to 2 of my velocity vector, and then minus the integral from 2 to 3. And again, we're doing minus to counteract the negative area. And you've done enough integration problems now that I'm just going to leave the answer like that. Oftentimes, once you sort of get your rites of passage with being able to do kind of simple integration, once you do those rites of passage, mathematicians will consider this a sufficient answer because any computer program, Wolfram Alpha or your calculator can compute this for us. So we don't need to spend our time doing those computations anymore. All right. Oops. So, I think one more problem and that'll be this video. So it says a velocity vector is given here, and at time equals 0, the position is 5. It says determine the maximum velocity of the particle. Justify your answer. Well, whenever we're talking about maximum velocity, that's or maximum value, think derivative. So we need to take the derivative of the velocity. Well, the derivative of the velocity is low d high, which is just 1, minus high d low, which is 2t, all over low. And famous Christina Michelizzi, probably getting a laughter right now, all over low squared. And if we simplify this, this gets 1 minus t squared over 1 plus t squared squared. And the idea is we need to see when this is 0 or undefined. And the fact of the matter is it will never be undefined because this value is always positive. So really we're just looking at the numerator. When is the numerator going to equal 0? So that's going to happen when t squared equals 1. So that happens when t equals plus or minus 1. All right, well, is it a max or a min? So here we make a derivative chart. So we get t and v prime, and we're going to put in, well, since I'm looking from time greater than 0, I don't need to worry about the negative 1. So I just need to look at time equals 1 and time less than 1 and time greater than 1. And we know at time 1, our derivative of velocity is 0. Time less than 1, choose like 1/2, and that's going to become a positive value there. Choose a value greater than 1, like 5. This becomes a negative value. So we see that it's a max. It's going to be a max at 1. So the maximum velocity of the particle, well, the maximum velocity occurs at time equals 1, and the actual velocity is plugging 1 in. So 1 over 1 plus 1 squared, plugging it into the velocity equation, of course. This is 1/2. So that's the fastest we go. The fastest we go is 1/2. Cool. So that's part A. How about part B? Well, let's put this on another page so that we can do the work a little bit easier. And we're looking at question B. So it says determine the position of the particle. Well, this is a great question. The position of the particle, if we're given the velocity, we're going to have to do some antiderivatives. And they give us the position at time equals 0, which is 5. So since they give us the position at time equals 0, we're going to integrate from 0 up until the time that I'm curious about, which is 3. And I'm going to integrate my velocity, which is t over 1 plus t squared dt. And, I look at this and I say, oh, okay, well, this is almost following into a derivative up top. So if I put a 2 here and then a 1/2 out in front, now we've got the derivative. Well, we got our function here and the derivative up top. So this equals 1/2 times ln of 1 plus t squared evaluated from 0 to 3. Well, simplifying this, we have so this equals 1/2 ln, and then plug 3 in, ln of 10, minus ln, putting 0 in, of 1. And we know everything about ln. We know that ln of 1 is 0, so that goes away. And then the key thing here, the really critical idea, is to relate this to the fundamental theorem of calculus, which says that this equals the position at 3 minus the position at 0. That this indefinite integral that we just evaluated was the change in position from 3 to 0. Fundamental theorem of calculus. So this equals s of 3, which is what we're looking at, or looking for, minus s of 0, which was given to us. It's 5. Therefore, we know that s of 3, solving for s of 3, our position at time 3, equals ln of 10 over 2 plus 5. Now, that doesn't look totally satisfying as an answer, but this is actually as exact of an answer as you can get. Cool. Um, Now, let's do C and D. So it says, for C, what's the total distance traveled by the particle from t equals 1 to t equals 3? Well, total distance here is going to be the same as the net distance. And why they're the same is that my velocity curve can never be equal to 0. My velocity, or less than 0. My velocity is always greater than 0 as long as t is greater than or equal to 0. So t equals 0, my velocity is 0. 0 over 1, 0. But for every value greater than that, we're going to get a positive value over a positive value. The velocity will always be positive. So as long as the velocity is always positive, you're always traveling in the same direction. Therefore, total distance equals net distance. So to find that value, we're going to integrate from 1 to 3 our velocity vector, t over 1 plus t squared dt. And we already did this integral, so we can evaluate that pretty quickly. We're talking about 1/2 ln of 1 plus t squared from 1 to 3. And now we just plug in. We have 1/2 ln of 10 minus 1/2 ln of 2. Now notice that we can simplify that. This is 1/2 ln of 10 minus ln of 2. And knowing what we know about log rules, that's 10 over 2. We can write that as 1/2 ln of 10 over 2. And further simplifying that using our power rule, that equals ln of 5 to the 1/2. Lots of pre-cal showing up. But that's a pretty problem. And to round out today's topic of problem solving with applications of the definite integral, let's just answer this very last question, which is to find the limiting value of the velocity as t increases without bound. In other words, we're talking about what's the limit as t approaches infinity of our velocity vector, t over 1 plus t squared. And we know that as t approaches infinity, the t squared is going to grow significantly faster than the t. If we want to prove that even more nicely, we could write this, and we've done these before, as divide everything by t squared. And when you divide everything by t squared, it really gets significantly simpler to evaluate this limit, because what we have is 1 over t, and then 1 over t squared plus 1. And as t approaches infinity, this roughly simplifies to 0 over 0 plus 1, which equals 0. So the limiting value of the velocity as t increases without bound is 0.